Let's explore each layer of the OSI model in detail, extending the discussion to include various practical aspects, examples, and historical context where relevant. 1. Physical layer. Layer 1. The physical layer is the foundation of the OSI model, handling the physical connection between devices and transmitting binary data as electrical, optical, or radio signals, medium and signals. This layer specifies the hardware that transmits raw bit streams over a physical medium. Key components include cables, coaxial, twisted pair, fiber optic, and wireless technologies. Each medium has its properties. Coaxial cables are known for shielding, twisted pair cables for minimizing interference, and fiber optics for high bandwidth and long-distance transmission. Data representation. Bits, zeros and ones, are represented differently depending on the medium, via voltage levels in copper wires, light pulses in fiber optics, or radio waves in wireless networks. Devices and technology. Hubs, repeaters, network adapters, and modems operate here as they manage the raw data transmission from one physical device to another. For wireless communications, components such as antennas and transmitters are involved. Transmission methods. It includes simplex, one-way communication, half-duplex, two-way, but not simultaneously, and full duplex, two-way simultaneous communication. Signal timing and synchronization. Bit synchronization ensures that data is appropriately separated and decoded upon arrival. Techniques like NRZ, non-return to zero, Manchester encoding, and others help direct these temporal aspects of transmission. 2. Data link layer. Layer 2. The data link layer provides node-to-node data transfer and detection and correction of errors that may occur in the physical layer. Framing. This mechanism packs bits into manageable units called frames and attaches headers and trailers, for start and end indicators, to help with the identification and error checking. Error detection and correction uses SRC, cyclic redundancy check, and other mechanisms to detect errors in a frame and sometimes corrects them with methods like checksums. Error correction is more common in higher layers except for correction methods like ARQ, automatic repeat request, which may happen on this layer. Flow control manages data flow between devices to prevent a fast sender from overwhelming a slow receiver. Techniques like stop and wait protocol and sliding window protocol ensure efficient data transfer. Protocols and technologies. Ethernet, wired, and Wi-Fi, wireless, are key technologies operating in this layer, in which MAC, Media Access Control, handles access to the physical transmission medium, determining how devices use a shared channel. MAC and LLC sublayers. 1. MAC determines how to take turns sending data over a shared channel, CSMA/CD for Ethernet, CSMA/CA for Wi-Fi. 2. LLC provides interface and control for network layer protocols, offering error detection and flow control. 3. Network layer. Layer 3. The network layer manages device addressing, tracks the location of devices on the network, and determines the best path to transfer data. Logical addressing assigns unique IP addresses to devices, differentiating them across networks. IPv4 and IPv6 addresses are examples, with IPv6 designed to address IPv4 shortcomings like address depletion. Routing determines the optimal path for data packets based on factors like network conditions, bandwidth, and congestion. Routers are pivotal components that direct packets based on routing tables and algorithms. Protocols. Besides IP, Internet Protocol, there are routing protocols like OSPF, Open Shortest Path First, and BGP, Border Gateway Protocol, dealing with intra-domain and inter-domain routing respectively. Packet forwarding involves direct transmission of data packets from source to destination through a series of routers, facilitating communication between devices on different networks. Techniques like packet switching enhance efficiency and reliability. Fragmentation and reassembly splits larger packets into fragments if they exceed the maximum transmission unit (MTU) of the underlying network and reassembles them at the destination. 4. Transport layer. Layer 4. The transport layer ensures complete data transfer across the network, providing reliability, flow control, and error correction from one end system to another. End-to-end communication facilitates communication sessions, providing services like error detection/correction and retransmission of data in case of errors, as well as flow control between host systems. Segmentation and reassembly divides messages into smaller segments that are then reassembled into a complete message at the destination. Headers in this layer provide sequence numbers for reordering segments. Flow and error control uses protocols to manage traffic, preventing congestion and managing data flow speeds. TCP effectively manages these aspects with techniques like acknowledgement packets, windowing for control, and retransmissions for reliability. Protocols. 1. TCP, Transmission Control Protocol, provides reliable, ordered, and error-checked delivery of a stream of data. 1. Known for its handshake process for establishing connections, flow control with the sliding window protocol, and segment retransmission. 2. UDP, User Datagram Protocol, offers a simpler, connectionless, and faster transfer of data packets without guarantee of delivery, ordering, or error correction, used in applications like streaming where speed is critical. Multiplexing utilizes port numbers to allow multiple applications to use the network simultaneously. Differentiates services and applications at the transport level using a port space. 5. Session layer. Layer 5. The session layer manages sessions in network communications, facilitating opening, taking control, and closing dialogues between processes. Session management establishes, manages, and terminates connections between applications. It works much like a controller in complex operations, allowing controlled exchange. Dialogue control manages exchanges between two endpoints, ensuring synchronization and orderly data exchange. It also determines the mode of communication, whether full duplex, half duplex, or simplex. Checkpoints and recovery provides checkpoints to manage sessions, so that data can resume from a certain point if a session fails rather than starting over. Authentication handles services like user logins and password verification, ensuring that the session should be initiated only after validating the identity of connecting entities. Examples. While explicit session layer protocols are less visible today due to convergence in higher layers like the transport layer handling similar functions, legacy networks have used protocols such as RPC, remote procedure call. 6. Presentation layer. Layer 6. The presentation layer deals with syntax and semantics of data interchange, translating data formats, encrypting, and compressing information. Data translation converts data into a format that the application layer can accept. This covers character encoding, such as converting ASCII to EBCDIC, or data serialization formats like XML or JSON. Encryption provides security for data privacy and integrity through methods like SSL/TLS encryption applied to secure HTTP sessions. Compression reduces the size of data to optimize and speed up transmission, which is crucial for media transmission, for example, JPEG for images, MPEG for video. Compatibility bridges differences between data representation on different platforms, ensuring that systems with different internal formats can communicate smoothly. Coding and conversion ensures that exchanged information is in a language or representation that can be interpreted by applications at the end systems. 7. Application layer Layer 7. The application layer is the topmost layer that interfaces directly with users and applications, providing services and network application capabilities. Network processes to applications allows user-level processes to interact with the network, managing protocols that deliver specific data services. User interfaces and APIs exposes interfaces and protocols that applications can use to request network services. Includes FTP for file transfers, HTTP for web access, SMTP for email, etc. Protocol examples. Besides the fundamental protocols like HTTP, FTP, SMTP, DNS, translating domain names to IP addresses, are crucial for maintaining robust web services and communication. Service definition and implementation ensures end users can interact efficiently with services, defining processes by which software can retrieve and send data. Data representation and response manages how data is presented to users or applications, dealing also with response caching and data logging for network requests. In modern networks, layers are closely integrated and often optimized, with some functions overlapping. Understanding these layers helps diagnose network issues and improve system designs by clearly defining the roles played by different technologies and protocols in data communication. This layered architecture also enhances focus on specific areas within networking, facilitating problem isolation and resolution.